Welcome to the MH2801 video segment on why complex Fourier series. Now, we've learned in the earlier video segment how to write down the real Fourier series, which is written as A0 for f of t, for the periodic for a function f of t that has period t. We write it as A0, a constant that is equal to its the average value of the function over one period, plus a sum from 1 to infinity an times cosine 2 pi nt over capital T, plus a sum from n equals to 1 to infinity of bn sine 2 pi nt over capital T. Now, the inconvenient part of having this real Fourier series is that we need to evaluate the coefficients a0, an and bn separately. As such, a0 is equals to 1 over t integral from 0 to t of ft dt. An is equals to 2 over t and integral from 0 to t of ft cosine 2 pi nt over capital T dt, and then bn is 2 over t integral from 0 to capital T ft sine 2 pi nt over t capital T dt. So we have to actually have to evaluate two sets of coefficients plus one single coefficient, which is equals to the average value. Now, wouldn't it be nice if we can somehow just evaluate one single Fourier coefficient, and then that we are done defining the Fourier series? And in fact, we can do this if we somehow write f of t, the real Fourier series, as a complex Fourier series. Now, to do that, all we need to do is to remember that cosine 2 pi nt over capital T is equals to 1/2 I 2 pi nt over capital T plus 1/2 minus I 2 pi nt over capital T, okay, and then sine of 2 pi nt over capital T is equals to 1 over 2i I 2 pi nt over capital T minus 1 over 2i minus I 2 pi nt over capital T. So if we rewrite all the cosines and the sines in this particular way, we can show that ft can be written as, well, the constant term can of course be written as a0 times e to the I 2 pi 0 times t divided by capital T, and then plus, because each of the cosines and sines become two terms, we're going to have altogether 4 different sums. The first sum is going from n equals to 1 to infinity of an divided by 2 e to the I 2 pi nt over capital T. The second term is plus, okay, again sum from 1 to infinity of an over 2 e to the minus I 2 pi nt over capital T. And then for the sine, there will be again 2 other terms, and going from 1 to infinity of bn over 2i I 2 pi nt over capital T minus a sum from 1 to infinity of but bn over 2i to the minus I 2 pi nt over capital T. Okay, so let me see. Yes, so now we can write this in a slightly different way. So we can write this term here because it's minus. So what we're going to do is we are going to write this complex exponential as e to the I 2 pi minus n times t divided by capital T, and we do the same for this particular complex exponential. And then the net effect would be, and then we change variables because these integers are negative, because here n runs from 1 to infinity, therefore the integers appear in this complex exponential are all negative, so we can instead replace this sum by a sum going from minus infinity to n equals to minus 1. Okay, and then combining these three, we will get a continuous sum from, so combining this term here, and this particular sum, where the minus sign is absorbed by n, we can write this as one single sum going from n equals to minus infinity to infinity of a n over 2 kind of and times e I 2 pi nt over t. Now we have yet to bring in, of course, the bn's, but we can do the same thing. We can absorb we can let n absorb the minus sign, so that the sum is a sum from minus infinity to 1 instead of from 1 to infinity. And then when we combine all the term by term, then we will find that f of t. So let me erase some stuff here, and so that make room for some discussions. So let me erase this, not so important. Okay, I don't want to clear page at this point in time because most of the results are on this page, and I wouldn't be able to remember some of the more intricate expressions. So I rather erase some stuff and then continue writing here. So if you need to see these formulas again, you can always rewind the video and see what they are, and then come back and look at this again. So in the end, so after all this stuff here, we can then write ft. Maybe I should change color. We can then write ft as a sum from n equals to minus infinity to infinity of Cn e minus ei 2 pi nt over capital T. Okay, so where Cn, if you take a look at these two expressions, Cn is actually equals to an over 2 plus bn over 2i for n greater than or equals to 0, and then except that for n equals to 0, this a0 have to be redefined slightly, and then Cn is equals to an over 2 minus bn over 2i for negative values of n. Okay, so this is how we can write a real Fourier series in terms of a complex Fourier series, and the relationship between the real coefficients and the complex coefficients are given by these two expressions. And now let us go on. So of course, obviously because Cn is related to an and bn in this particular manner, if we want to find the coefficient Cn, we can just go ahead, find an, find bn, and then reconstruct Cn in this particular way. But this is not the most convenient way. So in the next video segment, we will see the most convenient way to evaluate the complex Fourier coefficients.